Welcome to Drone System and Control course. In the previous lecture, we talked about autonomy, why autonomy is needed, different levels of autonomy. At the end of the lecture, we talked about artificial intelligence plays an important role in autonomous operation of these drones. In this lecture, we talk about some of the essentials of neural networks for aerial perception. Perception is a very important module for autonomy because the drone needs to see the context in which it is flying. It has to identify, and it also helps us to predict where the threat is and where the threat will come in a spatial and temporal location. How do we handle the threat? How do we generate necessary trajectory or detect the targets where we need to deliver certain actions on the targets, right? So for all these activity, perception plays an important role. So we'll spend some review aspect of it to understand what is these neural networks is all about, how it's useful for aerial perception activity, right? Let's understand what is artificial intelligence, what's machine learning and deep learning. If you need to understand more about this, you may have to take a course on AI or ML or DL. In this lecture, we are just giving an introduction to it so that we can go ahead and use such architecture for autonomous operation of the drones. Okay. So we will try to look at the fundamental building blocks of the neural network, the activation functions which is present, their importance, how this dense fully connected networks are built, what are its applications, how do we learn these weights of these neural network to do certain tasks, right? Then there are some problems associated with that, overfitting, generalization, underfitting kind of a problem, what is practically we need to do. Very important aspect, what is the data, how the data represent in the real space, what's the sample data, how do we approximate the distribution, right? The relationship, how the relationship is representing the entire distribution aspect of it, the impact of all this we'll just discuss in this lecture, right? So AI, what we meant, AI mimics the human cognitive functions, the ability of the computer or the machine to perform tasks. Typically, these tasks require human intelligence like learning, problem solving, or decision making, right? So when you see multiple drones flying in the same altitude, when the sensor see multiple drones, it has to decide whether these drones are going to be a threat or not. Threat in terms of what? Are they going to be a collision or not? Right? When you talk about machine learning, it's the ability of the computer or the machine to learn the relationship between the data and make predictions or decisions based on the data with being explicitly programmed or not, right? They learn from the experience and they use the data to improve the performance over time. For example, if you are talking about target detection, target recognition and classification activity or forecasting kind of a thing, I have a current position information, suddenly GPS is lost. I can use the recurrent nature of the system because we are looking at dynamical system. Can I predict what will be my next position based on the current sensing state? Can I identify my location, estimate my locations precisely, approximating the complex nonlinear relationship between the input and the states of the system, right? Deep learning, when I say, it's also a subclass in machine learning. The only difference is I don't extract the features and give it to the computer. I allow the computer to extract the high level features from the data, right? for a particular task, what could be the ideal high-level features that I could extract and approximate the relationship. Now, if I'm trying to give you in the notion, AI is encompasses the machine learning and deep learning inside, right? Teaching the computer to learn from task from a raw data, right? I'm providing a data and I'm allowing the computer to come up with a policy to fly the drone, right? I'm allowing the computer to ability to make decisions of conducting a task, not by the rules, right? Because these are uncertain scenarios, I need a computer to make decisions like humans, right? I need artificial intelligence. They represent these relationship in a complex form. Some are interpretable. Often it becomes a black box, right? It's very difficult to decide why it happened, right? So we need to understand the foundational block of this artificial neural network, and then we can look into how we can apply for autonomous aerial perception task, right? Now, just to give you a clarity on understanding, when I talk about feature extraction, I have a raw data. Me being an expert in that domain, I look at the raw data and trying to extract, like tailor cutting the cloths, right, for a specific shirt or for a person, right? I extract that and provide. That's the features. And that features goes into the network, and using the feature makes a prediction. I can have a supervised learning, which means I know the ground truth. I can use the relationship between the ground truth and the predicted information, update my weight. Sometimes I may not have the ground truth. I can determine the underlying pattern in the data and identify the data, right? That becomes unsupervised learning. Sometimes I may have few samples, some samples may not be available. I can look at a semi-supervised learning, right? Or completely reinforcement learning based. I can only get a reward for my actions. I can use the reward to learn the relationship, right? But here the main part you need to understand is the feature has been extracted. But if you talk about deep learning, I give the raw data to my network. I'll provide the prediction, ground truth, but I allow the neural network to extract the underlying features required to approximate the relationship between the raw data and the expected output. Okay, they just try to identify the features, transform them into higher level representation which is useful for approximating the relationship, right? That's what we meant deep learning, right? So all these comes from inspiration of human brain. The foundational unit of the brain is neuron. So what the neuron does, you have a dendrites which collect the signal and electrical signal. The electrical signal which goes into your main part cell body where the signals gets accumulated, right? And once it crosses a threshold, it produces another spike which goes out of this long axon. These axons, end of the axons are connected to other neurons. In a simple sense, it's more like an RC circuit, right? There is a charge, that's my input, and the charge flows into my capacitor, right? The capacitor receives the charge. Once the amount of charge received crosses a certain threshold, the capacitor opens and discharge. Right? The discharge will go out of the axon to the next neuron. Right? So this is the biological neuron. Inspired from that, what we have is an artificial neuron. We have input x1, x2, xm. These are m inputs. right? And I have the connections from these M previous new input neurons, and these input signals are weighted. This weight could be positive, means then it will be excitatory in nature. If the weights are negative, then it will be inhibitory in nature. These weights are modified, and then you sum the weights. It's basically what's happening in the cell body. That's a nucleus, right? All the signals amplified or suppressed, and that's available as a synaptic potential in the cell body, and which goes through a nonlinear function and produces an output y hat, right? The y, if I am representing in mathematical sense, my predicted output y hat is a nonlinear function of weighted sum of input signals. There are m signals, right? This is a basic building block of artificial neural network, right? Mathematically, if we represent y hat as g, j is equal to 1 to m, wj, xj, right? Now, this is not sufficient. We need a biased neuron. The biased neuron helps this neuron to approximate any function. Otherwise, you can just approximate something which is passing through the origin, right? So, we want the same structure, right? Input, synaptic weights multiplied by the input, that's your synaptic potential, which goes through a nonlinear function. But here we have an additional neuron, which is a bias input, which goes to your synaptic potential. In a mathematical sense, y hat equal to g w naught, that's w naught is a synaptic weight between the biased neuron and your nucleus, right? W naught plus summation j is equal to 1 to m wj xj, right? This is weight associated with your bias, right? If I am here, what happens is I can approximate any functions, right, using this bias, right? I can adjust the function to pass through any line. But we have to implement this in computer. I don't want the loop structure. Can I represent it in a matrix form so that I can handle this input vector very efficiently, right? So, we see that input is a vector of dimension m. Synaptic weights here is of dimension m, right? So, the bias input comes in. So, if you look at my weight vector including the bias w0, w1, w2, wm, which is m plus 1 vector. My x is also a vector, right, which is x1, x2, x3, xm, as well as the bias input 1. So, I can represent in a mathematical sense y hat is nonlinear function g, which is activation function, which is w transpose x, right. Now, this I can have a different activation functions, right. I can put a tan hyperbolic activation function, right, which is basically you project this input between plus 1 and minus 1, right. It can take any value between minus 1 to 1, right. If wx is greater than some value, it will always saturate to 1 or minus 1, right. In between it will have a linear characteristics, right. I can also use different activation functions. These activation functions are added into the artificial neural networks to bring some kind of a nonlinear relationship between the input and output. It also helps in approximating complex relationship between the feature x and output y. Because these activation functions, right, smooth and continuous, then I can have a gradient update rule. There are some activation functions which is not continuous. For that we have a different learning rule. We will talk about it later. More details on why these activation function and when it will be useful, one need to take a course on AIML itself, right. You have something called unipolar activation function. You have a bipolar activation function. You have a ReLU activation function. If you see in unipolar, the output is either 0 or 1. Whenever x is greater than 0, it is 1. Otherwise, it is 0. Or bipolar, I can say 1 or minus 1. When x is greater than 0, 1. Otherwise, minus 1. I can have a ReLU. Whenever x is greater than 0, it's x, right? Less than 0, 0. I can have one more limit. If x is less than 255, it is 255. X is less than 0, it is 0. Otherwise, x, right? So those are making sense when you are talking about image kind of data, right? I can also have continuous activation function in unipolar. I can put 1 by 1 plus e power minus x, right? It gives you between 0 to 1. I can have bipolar activation function, right? I can have a ReLU in that sense. This piece is continuous except at x is equal to 0 or x is less than 0, right? So that's the only problem. Single neuron to do a certain task, right? Let's assume there are 3 samples are there. Each sample has 4 features, okay? We are going to learn to find a pattern in the data. Let's say I am fixing an architecture. Here number of inputs are 4, x1, x2, x3, x4, right? And I wanted to have the output to be either 1 or minus 1. If the pattern belongs to a class, it is 1, otherwise minus 1. And I can initialize this weight randomly. I remember here the weights of the neural network cannot be 0. With 0, any input will become 0. So what we do is we initialize them very close to 0, right? And uniformly distributed around a small epsilon radius of small radius of epsilon around the origin, right? I am not talking about supervised learning, but I am talking about something called Hebbian learning. When a neuron is similar to the input, then the synaptic weight gets excited. If it's not similar, then it is inhibited. Let's use that kind of a learning algorithm, which means that my change in weight depends on eta and y into x. This eta is nothing but learning rate, right? Rate at which the synaptic weights changes for every sample. This y hat is nothing but your predicted output, right? X is the current input of sample, right? So I am going to use the simple Hebbian learning rule to demonstrate how one can learn this synaptic weights automatically, right? So I mentioned activation function, right? So I am going to take an output y hat. It's a bipolar, either 1 or minus 1. It gives 1 when W transpose x is greater than 0, otherwise it is 0, right? So I have input. There are 4 inputs, x1, x2, x3, x4. There are synaptic weights, okay? Just for the sake of an example, I am not initializing close to 0. I am just putting some value 1, minus 1 and 0.5 for W4, right? I am summing all this, I will get a synaptic potential. I pass through bipolar binary activation function. So if W transpose x is greater than 0, I will get 1 as an output, otherwise minus 1 as an output. That's my activation function, right? Now let's consider a scenario, right? Let's take an example. The first sample, right, is 1, minus 2, 0.5 and 0. This is my input x, right, x, and this is my initial weight vector w, right, w transpose x. If I do that, 1 into 1, minus 1 into minus 2 is plus 2, 0 into 0.5 is 0, 0.5 into 0 is 0, so 1 plus 2 is 3. 3 is greater, G is my bipolar activation function. When W transpose X greater than 0, I'll get 1, otherwise minus 1, right? That's my activation function. Since W transpose X is 3, which is greater than 1, I get output as 1. What's my Hebbian learning rule? New weight equal to old weight plus delta W. My delta W is eta y hat x, right? So new weight W is my old weight plus y hat into x. Y hat is 1, 1 into x, 1 into, I'm just putting it, and I'm assuming eta to be 1. So 1 into 1, 1 into minus 2, 1 into 0.5 and 0. So this is my new weight, right? My new weight is 2, minus 3, 1.5 and 0.5. I can update with the second sample. This is my second sample, x2, right? This is my updated weight, W prime. Now if I look at it, my W transpose X is negative. If it's negative, my Y hat is equal to minus 1. Which means, as per the Hebbian learning rule, W plus eta times Y hat and X, eta equal to 1, right? X2 into minus 1 is my delta W. So if I just take a look at it, this is my new weight. I can take the third sample, right? I can see the new weight into third sample, which is x3, right? This is my new weight W, right? W transpose X is minus 3. Since minus 3 is less than 0, so it is the output is minus 1. So again my weight get updated like this. I can repeatedly present these 3 samples again and again until there is no change in weight. At the end of it, if you see, I get a new weight. That weight will excite my input if it is similar to that. If it is not similar, it will inhibit. So if it will just predict the patterns which is all positive, and otherwise it will predict them as a negative. It segregate the pattern into 2 groups, 1 and minus 1. Okay. Now single layer is not sufficient to solve the problems, right? So I need a multiple layers. For example, I can approximate perceptron, what we have here, to OR gate, AND gate, or simple y is equal to mx plus e kind of a problem. But when the relationship become complex, it's very difficult to approximate them. So we may have to project the input x to higher dimensional space. In the higher dimensional space, we may be able to see the pattern much more efficiently, right? We can segregate them. So we need a multiple layer neural network, right? What I meant is input x1, x2, xm is there, and you have a weight w1, w2, and you have one output y1, right? It's not sufficient, so I will go for multiple layer. I have hidden layer h1, and then same inputs going through different weights, and I have one output hk, which is tan h of wk transpose into x. I could have multiple such neurons, h1 to hk. There are k neurons in this layer, and these k neurons can be connected to the output layer with a weight v. That's v is output weight. I can get an output. I can get one output. I can get n outputs also, right? So here if you see input layer, one hidden layer and an output layer, right? I can have multiple input layer, multiple hidden layers, right? And output layer. So that becomes fully connected. Wherever I am putting x mark, is fully connections between the input to the hidden layer, and then there are multiple hidden layers. Here if you see, there is one hidden layer, there is another hidden layer, there is another hidden layer, and then you have an output layer. So I have 3 layers here. So I can have multiple such layers. Now the problem is, if you look at a supervised learning, I have the input, I have the output. For this predicted output, I have a true values. I can take the error, but I am not sure how these errors are projected. I don't have the projection of this output in multiple layers. So I don't know the ground truth. So I need to find a learning rule through which I can update all these weights. Hence I can approximate the functional relationship, right? There is a functional relationship exists between the y vector, right, into x vector. I call theta. Theta is the parameters. Here the theta is your w and v, right, if all these are together as a theta. So I need to find this parameter theta such that the predicted output y hat is as close as possible to the true. This is predicted, this is actual. The difference between the predicted and actual is very small, right? I need to find these parameters. Now just not that parameters, I need to find out how many layers are needed, how many hidden layers. That's a second question is, how many neurons in each layer? Right? This is very important. So we need to fix the architecture. When I say architecture, the input layer, output layer is known. The input layer has how many neurons depends on the features of it. Output layer neurons depends on number of outputs. That is known. The user need to determine how many layers I should have. In every layer, how many hidden neurons I should keep, such that the predicted output y is as close as possible to the true value, right? The architecture definition is very, very important if you are trying to approximate a complex relationship. On top of it, you also have to select a type of activation function needed to approximate the relationship. Okay. So let's take a single hidden layer network for ease of understanding, right? I have input layer, m features are there. There are m neurons in the input layer. Okay. I have k hidden neurons, right, in the first hidden layer, and I have n output neurons in the output layer, right? The weights is a matrix here connecting the input to the hidden, that's a W matrix. From hidden to output, the matrix V. These two are my parameters that I wanted to estimate. I want to estimate these parameters such that my performance index J theta is minimized. What's my J theta? It's a mean square error, right? Squared error, y is the actual output, y hat, that's my f of x comma theta. This is my y hat, right? The difference between these two, squared difference for all the samples, should be minimized, right? That's my loss function. So what I want to do in mathematical sense, I want to find the weights theta star. I am assuming that there is an optimal weight exists. I want to find out that optimal weight. How do I find? Argument minimum of theta of loss function, which is between the predicted output and actual output. In a previous case I showed it's a mean square error, right? One can use different loss function. One commonly used loss function is mean square error between the predicted output and actual output, right? So this is nothing but 1 over n summation I is equal to 1 to n y I hat minus y whole square, right? I want to minimize this error. That's my j theta. I want to find out. So I can initialize my theta and update by minimizing this function to get the new theta and keep on repeating till I find a theta which gives minimum error, right? So what I meant is, let's assume there are only two weights, W0 and W1. I assume that the error surface is beautiful like this, smooth like this. In a real function it may not be smooth. I initialize my weight to some value. For that particular weight my error is somewhere here. Based on the error I take a step and get a new weight and again keep going till my error is minimum. In a practical life the error function will not be so smooth. It will be really complex, right? Which means we cannot guarantee that it will reach a global minimum. It can get stuck at local minimum. What will I do? I reinitialize the weight at different point again and continue this algorithm again and see where that is converged. There are various modifications are available over a gradient. I don't have to just perform a gradient. I can do a batch gradient. I can compute the gradient for the entire set of samples, or I can bring in regularizations or Hessians to improve. There are various modifications are available. I am not going into the details, right? But you need to understand the error surface is not going to be smooth like what you see here, right? And that will affect the convergence of gradient based algorithms, right? There are problems comes into picture. One of the important problem in multi-layer neural network learning algorithm, right? We talked about how we can just create a densely connected network and you can minimize by error function and update. The one of the important challenge in neural network is the generalization problem, right? There are two factors, in fact 3 factors influence the generalization ability. One is architecture, right? Architecture is if you make too many parameter to be tuned or too big a network, right? It will try to mimic the training data, it will not generalize well. If you put a too small a neural network, again the data may not capture and hence the network is not able to capture the relationship, which in turn affect the generalization ability. So this relates into the architecture problem. It should not be too big or it should not be too small, right? Finding optimal architecture is a challenging issue in neural network. The second problem associated with that, second factor associated with the generalization is how many times you present the data, training data, right? If you one time if you present the entire training data, we call this an epoch. How many epoch? If you train for too long, right, it start mimicking like a training data and then it will not generalize also. So the number of epochs also plays an important role in generalization ability. The third challenge, which is not in our hand in fact, is the training data skewness, right? We all assume that the training data is generated from uniform distribution, but unfortunately the data is not from a uniform distribution of the entire input space. It's very difficult to guarantee that. Once you say so, it will also affect the ability to approximate. In a simple sense, if you want to understand, let's say I wanted to differentiate between drone and a bird. Okay, I have a lot of data for the bird and very few data for the drone. Then what will happen is the network try to predict everything as a bird rather than a drone, right? So the skewness is also an important factor. Maybe before we move on the practical consideration, I'll just give you some idea on how we divide the data. Let's say if I have a data, usually we have a training data, and then you have the test data, right? We use the training data for developing the network, and test data is unseen data we'll use it for evaluation purpose. This training data we further divide into a subgroup train and validation. Okay. Test set we will not touch, right? So if you see, I divide the data into three. The division of the training data to training and validation is also going to play an important role, because you are going to make decision on validation performance, right? How good is your network? So the validation data should represent your training and test set, right? If not, it will also affect your decision making capability. Sometimes what we do is we divide the training data into 10 sets. We use 7 sets for training and 3 sets for validation. Sometimes we do 70% training data and 30% test data. It depends on how big your data set and all this, right? So remember, train and validation and test set is needed. Sometimes what we do when we are dividing the data into 10 sets and 7 sets for training and 3 sets for validation, we repeat this again random 7 sets 10 times we do and check how validation performance is on all the 10 trials and then take a decision about it, right? So that's very important. Sometimes we do 10-fold validation, which means we divide the 10, 9-fold we use it for training, 1-fold for validation. If the data set is too big, I don't mind doing 10-fold. The data set is only 100, 10-fold validation may not make sense. So this decision of how much samples to be used for training and testing depends on the size of the data set, right? That's a very important thing. Let's try to understand, let's say whenever I do training or testing or validation, I'm measuring some performance, right? So I have a performance matrix, right? Let's say for a classification problem, we will be talking about overall efficiency, if it's a classification problem. If it's an approximation problem, we will be talking about mean square error, right, or root mean square error. Sometimes we can use R to estimate also, if it's an approximation problem. Okay. Now let's try to understand architecture, right? I am assuming that we are just doing a single hidden layer neural network, so that I can explain very easily. In case of single hidden layer neural network, what we are talking of, number of hidden neuron is a factor, right? I am keeping rest of the parameter constant. Of course, the learning rate is also going to play a role, but I am assuming the learning rate constant, right? Epoch, I am giving sufficient large number of epochs so that it can learn, right? Now we are looking at architecture alone, right? Now if I do an experiment with number of hidden neurons versus performance, let's say we are looking at approximation problem, right? Performance versus number of hidden neuron. When the number of hidden neurons are too small, your training error, the cross one is the training, the circle is validation. Test data I don't know, see, because I don't have the ground truth, I can't use the test data to determine this, right? So training, what will happen is, if you keep increasing number of hidden neurons, your training error will become 0 at some point, right? But if you look at a validation error, it starts decreasing right? After some point it will start increasing. So if you see, this is my optimal number of hidden neuron, not, I mean, close to optimal hidden neuron. Beyond that, the performance of the network will be affected, right? Now this is on architecture. Remember, I am providing a sufficiently large number of training epochs, right? My data distribution is uniform. Okay. Now if I look at the effect of epoch, right, that is how much time that you train the network, and then if you look at it, it's number of epochs, okay, versus performance. So when the number of epochs increases, your training error will come to 0 at some point. But validation error will also keep decreasing. After some point it will start increasing, right? Then you know your optimal epochs is here. And again here this is true for fixed eta and fixed NH. If your NH changes, the point number of epochs may not be the same. You have to understand, moment if you increase the number of hidden neuron, number of parameters will increase. For example, single hidden layer network, right? If you look at number of parameters, input dimension, which is m cross nh plus nh cross n is the number of parameters in the output. So if you look at this, it is nh times m plus n, right? If you increase the number of hidden neuron, there are more parameters. When you have more parameters, you need more time to learn, right? When you have lesser parameters, you will be able to learn, you will reach the capacity quickly, right? So you have to understand that. Again, I am keeping an activation function constant in all my experiments. So you see, there are many factors influence this performance, right? So one need to have a fair bit of understanding on what kind of activation function to be selected, how my data distribution is. I will explain a little later how the data distribution affect, epoch, architecture, right? All these are factors, and your learning rate too, okay. Now there are practical consideration we take care to minimize the problem of generalization, right, effect. So we try to use regularization term, right, or we try to bring in dropout. Randomly we make some of the hidden neuron to be 0, which means they are not participating in the weight update, right, which will help. Sometimes we use momentum term to help in generalizing better, right. So there are various other approaches one can adapt to get generalization performances. Now let us look at the effect of data, right. I am going to explain this with a very simple linear equation, right. I am trying to find out the equation y is equal to beta naught plus beta 1 x. X is my input, y is my output, right. The x belongs to this purple space, which is unknown for me. The relationship is also unknown for me. The beta naught and beta 1 is not known for me, right. The problem here is the data distribution is unknown, right. The relationship between input and output is also unknown. We randomly sample the space. The sample spaces are represented by the smiley faces, okay. We make an assumption here. Whenever we do the sample space, let us say I am sampling only the blue color one, right, and get the data from that particular space. My assumption is this blue space represent the entire purple space, which may not be true, right. If and only if we do a uniform sampling from the entire area, right, otherwise it will be very difficult. I use a blue space and try to find an equation, and y hat is beta naught hat and beta 1 hat plus x, into x plus epsilon. Epsilon is your approximation error based on your random sample itself. If this equation, can it represent the two distribution space? Yes, if and only if the blue space where I sample represent the entire distribution very well, which we cannot guarantee for most of the problem space, right. So what will happen is the training data, that is why you often say that I need more data. More data also is a little risky. Let us say you ask for more data, I will give a same sample, some 10,000 samples of the same input and output relationship, right. Will it going to help? No. What we meant I need more data is I want more data representing the entire distribution. I do not want, it's often in medical problems you will get this issue. You go to a doctor and say you want to find out a cancer or not, and you go to a doctor, I want more cancer data. It's very difficult to get it. He can give you more data, because most of the data could be from nominal patients, right. So that is a challenge. Whenever you get a training data, you have to make sure that it is distribute very well in the unknown space, right, and it should be uniformly sampled so that that data represents the distribution. So the model will be very close to the true relationship, right. Again this what we are talking about approximation ability, right. The generalization ability depends on model complexity, which is architecture, how much time that you present the data, that is the epoch, what kind of activation function, the function selection, the model selection will also affect, right. So many factors comes into picture. Okay. If you take perception and planning course, in that they will be covering about neural network and these associated problems. Okay. But for our course, if you just understand this data distribution is one of the biggest challenge, is more than sufficient, because we will be using this for identifying the system which can be used to estimate the latitude longitude whenever there is no GPS signal, right. In a summary, we talked about machine learning, deep learning, how they are different. We talked about basics of the neural network. We talked about importance of the activation function. Then we talked about densely connected, fully connected neural network, learning algorithm. We did not derive the learning algorithm in detail. I am giving you a nutshell understanding of it. When we go into recurrent neural network in the next lecture, we will derive for one specific neural network which we will be using it. If you want to understand more about it, you can go to the reading materials. There is a very good book, Neural Networks and Learning System by Simon Hikins, or Neural Networks and Deep Learning by Michael Nelson. One of the book you can read for a better understanding. Okay, thank you.